What are you doing? Our iPad's in. What are you doing? Alright, it's still good. Well, now that Blake is done microwaving our iPad, and we've handled him, I'm here to talk to you about light. Light is more than just the light switches in your house. It's also electromagnetic radiation. Electromagnetic radiation can come in forms of gamma radiation, UV light, or even Wi-Fi. So let's take a look at the light spectrum. Now there are different types of light ranging from radio waves to gamma radiation. And the type of light depends on the frequency. The frequency is the number of wavelengths that pass by in a given second. So now, the types of electromagnetic radiation are radio waves, which can be used for radio or Wi-Fi. Microwaves, they can damage iPads. Infrared light is the light given off by heat. Visible light is the light that you see in your eyes, and it can range from red to violet. You see that in a rainbow. Ultraviolet light, that makes you tan, and it gives you cancer. Gross. X-rays can see your bones. That's used in the medical field a lot. And also gamma radiation is used in the medical field. It can help treat cancer, and it can create the Hulk.
All light travels at 300 million meters per second. And in this activity we have planned, it will allow us to observe wavelength and calculate the frequency by melting cheese. Step 1. Step 2. I will place the cheese in the microwave, and the melting patterns will tell us the length between the crusts. Melted cheese. Now there are 2 portions of melted cheese right there, and I'll measure the distance from center point to center point, which would be exactly 6 centimeters. 1 microwave passes through the cheese twice in 1 wavelength, so we had to double the 6 centimeters to 12 centimeters for our equation. Given that the speed of light is 3 times 10 to the 8th meters per second, and the wavelength is 0.12 meters, we can figure out the frequency by dividing the speed of light by the wavelength, which gives us 2.5 times 10 to the 9th hertz for the frequency.
Under intense supervision, Blake here is going to demonstrate how a rainbow occurs. When he sprays the water, all the water droplets, they refract the sunlight and split up the light into the visible spectrum colors.
Oh my god, strong rainbow much.
Shake it.
As shown in the previous lab, a rainbow is formed when white light enters a water droplet and, through refraction, separates into the individual colors of the light spectrum. These rays refract twice in the water droplet and bounce back in the general direction of the original light source. Therefore, in order to see a rainbow, the light source must be behind the observer, which in this case is Sauron.
Another cool thing about light is that when it goes into something that's different than what it is before, it refracts or bends. Each material has an index of refraction, which just tells how well it refracts light. If light goes from something that has a lesser index of refraction to something that has a greater index of refraction, the light will actually bend towards the normal, which is just this vertical line. If it goes the other way, when light is going from something that has a high index of refraction, it will actually bend away from normal, going away from the vertical line. That's what makes looking at fish in a lake hard, because the fish doesn't actually appear where it really is. So now if, sometimes not all the light escapes from the water if it's going from the water to the air. So if the light reflects at a shallow enough angle, it won't go out, it'll go back into the water. That's called total internal reflection. This is actually used in fiber optics technology, where light is run through a wire and it is totally internally reflected until it goes all the way to the other side. You see this flower here appears red because it reflects only red light and it absorbs all the other ones. And then this green here absorbs all the light except for green and reflects that. So there are two types of primary colors. The first one I'm talking about is subtractive, which combines all of them, magenta, cayenne, and yellow, to make black. This happens because when you combine any two of the colors, fewer and fewer rays of color can actually reflect. They get all absorbed until you combine them all the colors. None of the light can reflect, so it appears black. For the additive, on the other side, that's the kind that you see on TVs, like the pixels have red, green, and blue. So when they are combined, more and more light rays of color can be reflected and fewer are absorbed until they all combine to make light. That's why if a light is shined through a prism, it separates back into all of its original colors. Magnification with mirrors can be modeled by ray diagrams. Now the way to create ray diagrams is, the first step is to create a parallel line from the top of the object to the mirror. And the second step is to bounce the line through the focal point. The second step is to go from the top of the object through the focal point to the mirror. And then make a parallel line. The intersection of these lines will model the height of the new object. Now, since this is an upside down image, that says that the image is real and it can be projected. And notice that with the concave mirror, the object is smaller. Now, we can calculate this, the height of this new image, by the equation 1 over f equals 1 over q plus 1 over p. And these variables mean focal length, magnification height, and object light. So we just need to insert the values that we know, and then we can calculate for the value that we are solving for.
Na 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 na.
Hey.
Na 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 na.
Hey.
Hey hey hey.
Hey.
Goodbye. Na 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 na.
Hey.
Na 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 na.
Hey.
Hey hey hey.
Hey.
Goodbye. Na 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 na.
Hey.
Na 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 na.
Hey.